Do y'all ever wonder what goes on in your brain? Those late night cravings for Taco Bell, or those random trips down memory lane? Personally, people tell me they wonder what goes on in my brain, usually after I speak. In my lab, we work to uncover some of the many mysteries behind the brain. One of these mysteries is the mechanics and specifics of how the brain communicates. We know that brain cells, or neurotransmitters, send text. Brain cells, or neurons, send text, or neurotransmitters, in order to perform certain functions. We know their words and their meanings, but we're still trying to piece together the exact sentence. In my lab, we were trying to answer the question that if we change some of the words, is the overall function still the same? That is what I set out to discover. Now I'm going to present the hypothesis of my experiment, that we hypothesized that the mice injected with the excitatory strain would habituate more than the mice injected with the inhibitory strain due to the differences in the efficiency of the glutamate signaling. But here's what that really means. Glutamate, or as I like to call it, dopamine's quiet cousin, is the most common excitatory neurotransmitter in the brain. It is involved in higher order functions like learning and in memory. In the region I studied, the VTA, 65% of the neurons relate to dopamine, but only 5% relate to glutamate. This has led to a large discrepancy in the amount of research between the two. But is this discrepancy validated? That is also one of the questions I chose to work out, so therefore I studied glutamate. Now I want to break down the signaling part, more specifically these three terms. Since we couldn't break down glutamate directly, we instead had to manipulate, through a special kind of virus called AAV, we manipulated its transporter. Now, we used two strains of the virus, one that would excite the signaling and one that would inhibit it. Now I'm going to break down the main verb in my thesis, my hypothesis, habituation. For this, I want everybody to close their eyes. I want you guys to get in your car, turn on the ignition, start driving. Go out the neighborhood, take a left on a South Harrell's Ferry, drive for a little bit longer, and then turn into a familiar restaurant, Cane's. Now you're in the drive-thru. The cashier asks you what you want, and you tell her you want a cognac combo. But of course, you got to sub the coleslaw for extra toast. Now I want everybody to open their eyes. I want you guys to smell this. Smell the chicken, the toast, and the fries. Smell it filling your car. But what happens as you keep driving? You'll notice that the scent it's a little fainter. It starts to fade a little bit. Why is this? It's not like it gets any weaker, but you don't smell it. This is the base principle of olfactory habituation, which is defined as the decreasing response to a once novel scent. So in this case, my brain has processed that I've got the canes. It is now storing that information so that I can focus on things like driving. And finally, the animals we experimented with were mice. Now we used two strains of mice. Wild type, which is just like regular mice you would find out in the wild, and mutant, which were these lab mice that were a little bit inbred. And the reason we used two strains was not only to provide a larger basis for comparison, but even before we gave them injections, we found that their response to habituation had differed. Now that I've broken down the hypothesis of my experiment, I'd like to show you how I went about it. We took the mice to something I like to call the arena. Now, it wasn't as cool as WWE's Monday Night Raw, some people would say. I personally like to think it was a little cooler. It looked something like this. Here, we would let the mice run around for 1 minute, and we would expose them to various different scents in something called the boat, which is denoted by the red circle. We would expose them to 5 different scents: banana, almond, water, and same in opposite-sex urine. We'd expose them to each of these scents 3 times. After that, sadly, the mice's time would have to come to an end. Now, I'll spare you all the details because I know all of us just ate, but I can promise you that they didn't feel any pain. After we had extracted their brains, they were ready to get sectioned. Now, when I say that, it means we had to take them to the cryostat room, which is in this weird part of the lab that smells kind of funky, probably because of all the amount of animal tissue in there. But sometimes one, aka me, needs to take one for the team. So I went, slicing and slicing their brains, just like how they do in the delis. And after many days of work, I finished. But for reference, I was slicing at a width of 50 microns, and 1 millimeter is 1,000 microns. So these things were razor thin, meaning I had to operate at the utmost precision. But after I'd finished, the sections were ready for their final step, immunofluorescence. Now, immunofluorescence is a two-part word. Immuno, which refers to the fact that we used antibodies, and fluorescence, which refers to the fact that when we expose these antibodies to a special type of microscope, they would light up. The result is a pretty image like this. And here's the VTA, right there. And based on what we would see in this image, we were able to confirm or deny whether what we had seen in the behavior was actually due to the injection or due to something else. After looking at about 40 of these, we were able to successfully confirm that all of our injections had in fact been in the right place, and that the behavior we had seen was due to the manipulation of the glutamate transporters. And we got results like these. Pretty much, we had as the y-axis the frequency of our visits, and then the different scents on the x-axis. But the key takeaways are that the VTA reacts differently to injection based on the mouse strain, which could suggest that the communication and expression of glutamate neurons varies between strains. And while none of the mice really consistently habituated, future work is being done in my lab to overall improve the experimental design, so that way we could get more consistent habituation and thus more consistent results. But I do believe my research helped connect a few pieces of a much larger puzzle in understanding how learning and memory works in the brain. Thank you.